than 88.86. Okay, so you are going to apply your stress critical is equal to P divided by A. Okay, so on the left hand side, basically, if your L over R is less than 88.86, no need to do or no need to perform buckling analysis. Sorry, I better write bigger. I write bigger. No need to perform buckling analysis. Okay. If your L over R is greater than 88.86, okay, structural analysis is based on what? Buckling now. Okay. So how we calculate the stresses are both what? Different now. You can see that, right? Okay. So if your L over R is greater than 88.86, you have to clear out buckling is less than that. So what is the trend? Okay, the trend, right? If you were to plot out the trend, so the trend will look like this. Okay, so the trend will look like this. When L over R gets bigger and bigger and bigger, this is just a sketch. Okay, your critical load, what will happen is your critical load decreases. You can see the higher your L over R ratio is, the lower the stress allowable is, right? What if it's less? If it's less, it can take what? The critical load is what? 250 times 10 to the power 6 Pascal. If L over R is greater than 88.86, your critical load, okay, your critical load or your critical stress will be reduced. Okay. So this is why this chart is important. Okay, this chart is important in this sort of analysis. Okay. So this again, this chart over here, okay, is for what? So this chart over here that you can see, this is only valid for pin ends condition. Okay, pin ends condition with Young's modulus is equal to 200 times 10 to the power 9 Pascal, and stress critical is equal to, or allowable or critical is equal to what? 250 times 10 to the power 6 Pascal. Okay, this is where this chart is valid. If not, yeah, it will not be a pin end. Okay, I want to look at another another example. Anyone, any questions so far regarding the chart and regarding what is important in this analysis, which is your critical load and your critical stress? Anyone, any issues for now? Okay, I don't see. Now, remember, whenever you provide the answer to your client, okay, they will ask you, how heavy can this structure take, or how much force I can apply. They don't ask you how much stress the structure can withstand, because we as human, we like to be able to relate physically, yes or no. Stress is difficult to relate physically, but weight is, right? So they will tell you, if I'm going to put 10 kilogram weight buckle, if I'm going to put 50 kilograms weight buckle, and you have to come up with an answer, and the best answer is based on what? Critical load. Okay, so that's why when we derive the expression initially, we derive based on what? Deflection, yes or no? You cannot tell a client, okay, in order to prevent buckling, make sure your deflection is not more than 3 millimeters. He or she will not know, right? How much force do I need to apply to get 3 millimeters deflection? Okay, that's why you have to tell them the load. Okay, okay. Next example it looks innocent but not so innocent. Okay, sorry, I have to say that. Some of you have been to courses that I teach. I don't do easy examples. I do complex examples. Okay, so let's look at this example over here. Okay, and this example, as I said, it looks innocent, but it's not. Okay, yeah, it looks innocent, but it's not. Okay, so coming to here. Okay, so what you see is this is the cross-sectional view. Okay, this is a cross-sectional view. It states that the effective length, okay, I want you to get used to this term also, effective length. Okay, so the L over here is 6 meters. Okay, and it's made out of 3 plates as shown, and E is equal to 200 times 10 to the power 9 Pascal. Okay, so that is given to us. So what they want us to find out is we have to determine the factor of safety. Okay, we have to determine the factor of safety. Okay, with respect to the centric load. So this load has been applied. Okay, this load has been applied in a centric manner. Okay, the fact that it's centric means what? When it's deforming, centric means during deformation, or during loading, sorry. So during loading, the load will always be in line or parallel to the centroid. Okay. So as I said, this question has a lot of layers. Okay, it looks kind of innocent, but it's not so innocent. Okay, so factor of safety is equal to P critical over P. Okay, where P is the what? P is the applied load. And for this case, the applied load is equal to 16 times 10 to the power 3 Newton. Okay. Right. So the formula that we are going to use, okay, let's look at the formula is straightforward. Okay. So the formula that we'll be using is PCR is equal to pi squared EI over L squared. Okay. We cannot use the slenderness ratio. In order to apply L over R, it has to be stressed, right? If you look back at the formula over here, in order to use the L over R, it has to be a what? A stress, because the L over R slenderness ratio is a stress, okay, because we have to divide by area. For PCR, you have to use what? Pi squared EI over L squared. And I hope this is clear for all of you. Okay, so we have to do it. Now, so this is in fact a 3D problem. Sorry, yeah, this all structures are 3D. So I'm going to sketch for you how this looks like in 3D. Okay? So the structure will look like this. Yeah. Okay, so this is how the structure will look like. And then we have a load applied on the, before I draw the load, I'm going to draw the centroid, the vertical centroid. So I'm going to take this as my vertical centroid. Okay, so that is our vertical centroid. And then we have a load coming down. Okay, this load coming down is 16 times 10 to the power 3 Newton. So from here, I'm going to draw our transformation, because this is a 3D problem. Okay, I'm going to draw our transformation. So we have, I'm going to call this our Y. Yeah, I'm going to call this our Y. This is our Z. And going up is our X. Okay, so that is the transformation that we are going to use. So if we look at the cross section, if we were to relate this to our cross section, this will be our Y. This will be our Z. And this is our rotation about X. Okay. Now what I propose, we go for a 5 minutes break. We come back, we continue with this problem.